Acrolab. Okay. Hey, we got it.
Cool.
All right. Thank you. My apologies. I'm a little slow. Okay. We're going to start talking about traditional thermodynamic equations and condensed matter. The gas law is the sort of primary or initial way in which condensed matter physics started, and we're going to talk about that for the most part today, and we're going to move on hopefully later to more aspects of it, and we're going to move into statistical mechanics and then finally go on to Maxwell's demon and the definition of thermodynamics in terms of information. All right, so we're got a little history of what I'm going to be covering. Thermodynamics initially started with steam equations, and in the 19th century, Boltzmann introduced the idea of statistical mechanics and the idea that complex microscopic interactions would emerge by averaging, which we often call coarse graining, and define ensembles and many of the things that we'll talk about next week. In the last quarter of the century, the development of information theory found a different description of entry, which up to a constant seems to provide a connection to thermodynamic entropy. And it was Maxwell's demon, which many physicists really felt was a problem until about 1960, where Maxwell's demon was finally subdued. And in the last 5 or so years, using Maxwell's demon, we've actually been able to unite physical entropy and informational entropy. So let's start with the early 19th century discoveries. And by the way, at any time that I'm saying something that doesn't make sense or you want questions, just interrupt and ask me. So prior to the 19th century, there were a number of people who developed various experimental laws. The first was in 1627 or 1662, actually. Robert Boyle created what was called Boyle's Law, and we'll talk about that a little bit more. And in 1787, Jacques Charles generated what was known as the Charles Law. His experimental work was done in 1887, but he never published it. It was Joseph Gay-Lussac, I don't know if I pronounced that correct or not, in 1802, who published the mathematical law and credited it to the unpublished work. And it's then called Charles' Law. And lastly, Lorenzo Avogadro in 1815 had an insight about the number of molecules that there would be in a gas. So these three, I'm sorry, is somebody asking a question? Oh, okay. These three laws provide the empirical equation of state, or the ideal gas law. And in the next subsections, I'm going to describe these laws, the ideal gas law, and a little bit more about equations of state. So, thermodynamics defines what are called state variables. And state variables are very specific and, at least to me, a little bit strange kinds of properties. If you have an extended object, such as a volume, a solid, a liquid, or a gas, the state variables are completely independent on the geometry of the object. So one such state variable is the volume. If you think about it, you know, you could have a cube or a sphere or a peanut, and whatever it is, they could all have the same volume. The physics about the state variables does not matter at all about the manifold. It's simply the volume of the nominal manifold. So that's rather different from other ways in which physics operates. So a second thermodynamic state variable is pressure, and pressure is force per unit area, which I've shown as an arrow, a force arrow hitting an arbitrary area, and pressure is the ratio of those two. Now, the area does not need to be a planar area, as I've shown it here. It could be the interior or exterior of a balloon. So here's a balloon that I have bouncing around, and that would work just as well. So we need to understand a little bit about how the pressure works. The first thing you need to do is understand about the tangent and the normal. So this line, which just touches that balloon or what potato, whatever you want to call it, which has a volume V, that is the tangent line, and perpendicular to it is the normal line. And the reason that that's important is that forces may not apply, you know, orthogonal to the object. I've shown it here coming in at an angle. So when you're trying to understand the force on the area, you need to break it into components. The component that goes along the tangent is irrelevant to the pressure. It's only the component along the normal that creates the pressure. So in thermodynamics, the typical types of condensed matter are a gas, a liquid, a solid, and three laws, Boyle's law, Charles' law, and Avogadro's law, apply for all types of condensed matter. So let's consider Boyle's law. We've said that the volume is independent of the shape in which the gas is contained. So to make it easy, let's use a piston that we can change the volume by pressing it in, and we can pull it out and change the volume in there. And the volume is very simple. You have the area of the cylinder times the length of the piston, and that gives you the volume. So if we did a series of experiments, we could choose various sizes of position of the piston. And as I said, the volume of the piston is the length times the area of the internal circular size of the piston, pi r squared. So the volume is pi l r squared. And for each of the lengths, we attach a weight to the balance, to the end of the piston of each of the separate lengths. So this is the idea of the three experiments that we're doing. So we have one weight, then we have two weights, then we have three weights. In each case, the volume is reduced because there is more pressure on the area. But Boyle's law, when you do this experiment, you find that the pressure times the variable in all cases is exactly the same as long as the temperature doesn't change. So Boyle's law, yeah?
Can I just interject a point here? I think Boyle's law is certainly true for an ideal gas, but it's only approximately true for a real gas.
Yeah, I will get to that considerably further along. I'll talk about van der Waals and other things like that. But I'm starting with the simplest case, the ideal gas law. So Boyle's law says that pressure times volume equals a constant. And Charles' law has a similar experimental setup. You fix the weight on the piston, but you don't change the weight, you simply change the temperature of flame on the piston, for example. And you then measure the corresponding volume that results. And if you do it for 3 different temperatures, you'll find 3 different volumes. But the ratio of the volume to the temperature is again identical. So as long as the pressure doesn't change, the volume is proportional to the temperature. And Charles' law says that volume over temperature is equal to a constant. So the temperature we're talking about is in degrees Kelvin. These are absolute temperature. So they're essentially 273 plus centigrade degrees. And if you double the absolute temperature in Kelvin, then the volume will double. Avogadro found that if you held the pressure constant and you held the temperature constant, then the volume is proportional to the number of moles of the gas. The mole. Well, a mole is a fixed number, n sub a, of molecules of a gas. And in fact, it's the same number for all gases. So this is a unit that's used, that every gas uses. And just like when you go to the supermarket, you buy eggs by the dozen. So Na is a unit similar to a dozen. But Avogadro, when he posited this number, didn't actually know what it was, but he knew it was very large. It, in fact, took about a century before physicists actually measured Avogadro's number. And the important insight that Avogadro had was that if you had different gases at the same pressure, temperature, and volume, then all of them had exactly the same number of molecules in the container. And you have to remember that at this time, people didn't believe atoms or molecules actually existed. They were something that people didn't think were real. But Avogadro thought they were. And it turned out he was, of course, correct. It wasn't until Einstein in 1905 showed that atoms were real in his paper on Brownian motion in 1905. So what's an equation of state? Well, you know you have a fixed set of state variables, and for the gases that we're talking about, their pressure, volume, and temperature. So an equation of state is a function, a function of the pressure, volume, and temperature, which equals to 0. And this characterizes all of the qualities of the condensed matter that we're dealing with. And the equation is known as the equation of state. Now, initially, equations of state were based on experimental results such as Boyle's laws, Charles' law, and Avogadro's law. And we're going to talk about for most of the discussion, we're going to talk about this meeting. We're going to talk about the ideal gas law. So the ideal gas law is really very, very simple. If you have the 3 state variables, then the equation of state simply says that the pressure times the volume is equal to nu, which is the molar number of gas there is. R is the gas constant, which is a universal constant, and T is the temperature in degrees Kelvin. So what are the units of the equation? Pressure, of course, is force per unit area, so it's newtons per meter squared. Volume is meters cubed. So when you take the pressure times the volume, you have newtons per meter squared times meter cubes, which gives you newtons times meters, which gives you energy in joules. So ultimately, the ideal gas is simply a conservation of energy. So there are only 2 independent state variables in the equation of state. You can determine pressure in terms of temperature and volume. You could determine volume in terms of temperature and pressure. You get temperature in terms of pressure and volume. So any of these, there's only 2 independent, and you can choose whichever 2 you want to. Typically, most physicists will talk about pressure and volume, and determine temperature from the pressure and volume. So we can use the equation of state in order to get some insight into the macroscopic physics and compare it to microscopic physics. Avogadro's number is about 6.01 times 10 to the 23rd per mole. So it's a huge number. That's a 6 with 23 zeros after it. And a billion has 9 zeros. So a billion billion, well, a trillion is 12 zeros, and a trillion trillion would give you 24 zeros. So this is almost a trillion trillion as the number of molecules in a mole of gas. Another link between microscopic and macroscopic physics is given by Boltzmann's constant, and that is simply the gas constant divided by the Avogadro's number. So it gives you 1.38 times 10 to the minus 23 joules per degree Kelvin. So it's got 23 zeros before the 138, 0.23 zeros and 138. Another way of understanding the gas is via the mass. So now we finally go to a particular gas, and let's say it has a molecular mass mu. Then the molar mass is simply the molecular mass times the Avogadro's number. So the total mass is given by the number of atoms times the molar mass, or the number of moles times the molar mass. So there are different variants, as I said, that you can use to look at the gas law and get some understanding about what's going on. So the first one,
Robert?
Yeah.
Quick question. Did they figure out the gas constant first, and then Boltzmann figured out that his constant was related to the gas constant, or how did that work?
I don't know. Steve, do you know?
I'd have to think about the historical sequence there. Off the top of my head, no, I'm not quite sure what the sequence was.
Thanks.
Yeah, I'm sorry. I don't know. Okay. So the first form is the way in which we take it by using Boltzmann's constant. So instead of PV equals nu RT, we can say that it's the number of molecules times Boltzmann's constant times temperature. But this is giving us an information about what's happening about individual molecules in the N is the number of total molecules in the gas that you're dealing with. So it gives you some insight into the microscopic physics of the gas. The second one is to look at P equals nu RT over B, or you can again take rho being the gas density and times the gas constant times the temperature divided by the molar mass. And so the gas density is the molar number of moles times the molar mass divided by the volume. So it is constant generally in gases. So we're talking about a local phenomenon. It is true just about everywhere in the gas. And that's again due to the fact that we're dealing with these strange kinds of variables called state variables. So, okay. So the first version is microscopic because we're counting all the molecules times the energy. The second version is not microscopic. I'm sorry, it's supposed to say local there. I screwed up in the typing here. I apologize. Here we're assuming that the pressure and temperature are the same at every position in the gas. The last one is pressure is, of course, what we had before, n times Boltzmann's constant times temperature divided by volume, where times, which is equal to a number density times Boltzmann's constant times temperature. Number density is just the number of atoms divided by the volume. So again, it's a quantity that is both microscopic because it talks about the number of atoms that there are in the gas, and it's local because it's assumed to be the set, not only assumed, measured to be the same everywhere in the gas. So for air at atmospheric pressure and typical temperature, we know that the pressure is about 101 kilopascals, pascals, I guess they are. Anyway, 1.01 times 10 to the 5th pascals. Temperature is about 295 degrees Kelvin, and mass is about 0.029 kilograms per mole, an average of nitrogen and oxygen, and there's roughly 80% nitrogen and 20% oxygen. So I'm giving 3 homework questions for you to work out on your own. And what is the volume for 1 mole of air at these properties? What is the density rho of the air? And how many air molecules are there in 1 centimeter cubed? Now, I've given you here rough answers. The first one is about a 40th of a meter cubed. The second is about a kilogram per meter cubed. And the third is about 2 times 10 to the 19th. However, the actual results are in Appendix 2, and you should try to work out these computations based on understanding how the ideal gas works. And after you've gotten results that are close to these, you'll know they're correct. And eventually, if you want to, you can take a look at Appendix 2, which has my results of those calculations. Okay, that's the end of this particular. I ran out of space in this. Oh, yes. for those who want to look into the appropriate Wikipedia entries, you can find one for Robert Boyle. It's here. When I send the presentations out, then you can just click on the three entries and they'll take you to the right place in Wikipedia, and you can read about Robert Boyle, Jacques Charles, and Avogadro. I'm hopefully now going to switch to a second presentation.
Could I ask a question?
Yeah.
I just want to get a little clarification from my, if I understand this. Are you saying that each gas behaves differently depending on the volume and the pressure and the temperature applied to it?
No, I'm saying that for many gases, not all, the properties of the gas are identical. They're
okay. So regardless of the elements of which the gas is composed, all gases behave the same.
Well, roughly. I mean,
roughly.
As we're going in the next presentation, we're going to talk about some other types of states of equations of state, including van der Waals, which has a different version, but to a first approximation, almost all gases behave like the ideal gas law, but only to a first approximation.
And in the beginning, when you showed us the cube, the circle, and the peanut, and all gases within those containers would behave the same. The volume would be the same within those different containers, regardless of the gas, approximately. I know you're going on to give us some exceptions, but
right.
Is that correct?
No, that's exactly the point. Whether you have a piston, or you have a peanut, or you have a sphere, or you have a potato, whatever its container it's in, the properties are the same on all of the for whether you have air or you have argon or some other thing. Now, the mole number, that's specific. The number of atoms or molecules is the same, but the mass of each individual gas is different. So so the molecular mass is different for each of the gases, and what's in the calculation of the number of moles in a particular gas. Okay, let me, I apologize, I have to get out of this because for some reason, why am I not getting out? All right. Why am I?
Do you have an escape?
Oh, pause share. There we go. That should. And a new share. If I now. Oh, come on. All right. I will just move differently. I don't know what I'm doing wrong here. Oh. All right. Let's go back to that. Share it. Okay. Now, if I escape, I get out of that. Good. Finally. All right. Now I can find the other presentation and put that one up. There it is. Okay.
Bob, we're still seeing the first presentation.
Yes, I know.
Okay.
I'm messing around behind trying to get it open. And yay. Hopefully now you're seeing the 1B version. Is that true?
No, not yet.
No. All right. So now I'm going to resume share.
There it is.
Yep.
Got it.
There it is.
Okay,
1B.
great. Thank you. All right. Sorry. Okay, so we're going to talk about the PV plane, more complex versions of the equations of state, and some equations of states that are not pressure, volume, and temperature. And then that was all I was able to put together for today. So we'll move on about what we're going to do next week. The abstract is the same as what we had before. So what I'd like to do is to show what the three-dimensional manifold of the ideal gas law looks like. So we know that the each point is the pressure, volume, and temperature. So we can then, in order to see how Boyle's law works, we'll intersect that manifold with planes of constant temperature, and that'll show how the various relationships are between pressure, volume, and temperature. And then again, as I've said before, only two of the independent variables, there are only two independent variables in the ideal gas law, so you can characterize it just using those two. And typically, we won't use the three-dimensional version, we'll use a two-dimensional version. And typically, it's the pressure-volume plane. You could also do the volume temperature plane or the pressure temperature plane, but almost everything in a thermodynamics course would be done in the pressure volume plane. They're all equivalent. Okay, so, oh, I'm sorry, I'm ahead here. Let me now share my movie. Here is my movie. And I'll share this. Okay. So hopefully you see the geometry of the ideal gas law.
Yes.
Okay. Then the ideal gas law is the pressure times the volume equals nu times R times T. I'm using units where nu equals R equals 1. This is what the ideal gas law in 3 dimensions looks like. I'm rotating it around simply to have you understand how it is. It obviously only fits in the one corner. It is not. This is simply for illustrative ideas, not how you couldn't actually rotate it and keep these axes constant the way I have here. And the next thing we're going to get to in a few seconds is where I'm going to start taking planes of constant temperature and showing how those interact with this three-dimensional manifold. So we'll take a look at those. And as you put the plane there, you see that it starts cutting at a particular place, and you get a line that goes there. And then you can start another constant pressure, constant period of time, and that will also create a line where the intersection was, and you start another plane going through, and you get another line in the space there, and then the last one that I'm repeating again. So when you're all done here, you have these four lines. Now, a PV plane would be the one down at the bottom here. You can project this down in each of the planes, and that's what I'm going to show in the next set of slides that I was showing. That's typically the way in which people look at it, is not in the three-dimensional version, but in the two-dimensional. So if we go to the PV plane, I can see that this is not a great deal because it's a little, the typing is very small. I apologize for that. But anyway, here we have the volume along the bottom and the pressure at the top, called the PV plane. And at any particular point, you can calculate what the temperature is. And in the units that I've been doing, I have the pressure at 0.9 and the volume at 0.1, so the temperature is 0.09 because I've used these strange units here. So what happens if you have a pressure that is constant? That would be Charles' law, and the pressure has to remain constant, so you just get a line that is a straight line that parallel to the volume here at a constant pressure. But when you're down here at the initial volume, the temperature is 0.08, but when you're down here at the volume 1, then the temperature is 0.8. So the volume went up by a factor of 10, 0.1 to 1, and the temperature goes in exactly the same way, 0.08 to 0.8. So whatever the volume is enlarged by a factor f, then the temperature's enlarged by the same factor. And what do we talk about if we have the temperature constant? This is Boyle's law that we talked about before. Here we have the same PV plane, but we have hyperbolas, which are only roughly parallel. And so for each line here, the temperature is a constant. For this one, it's 0.2. For this one, it's 0.4. This one's 0.6. This one's 0.8. So these are, again, at every point along those lines, you have all of the exact, you have the same constant, and you have the same properties of the gas here. So let's look at a few other PVT equations of state. If we have a transition from steam to a liquid, we know that water is roughly an incompressible fluid. So that means that the density is constant. The volume is, the molar volume is a constant. So the volume is independent of pressure and time. And that's what it means to be an incompressible fluid, that the volume is independent of the pressure and temperature. Now, another different equation of state for gases, and this is now one that's a little bit more complex, was proposed by van der Waals. And he proposed that the equation of state depended on intermolecular forces, and he has two constants, A and B, and those constants are different for each type of gas. So van der Waals' equation of state says that the volume minus a constant times the number of molecules in the gas times the pressure plus a term which is, again, a constant A that depends upon the gas, but it's divided by the volume squared. And then, of course, we have back the N Boltzmann's constant times time. So if we expand this, we have the initial term is PV, and we have NTKB, that's the other portion of the ideal law. So we have those two terms. We have another three terms, which are all multiplied by these constants A and B. So if for a particular gas, A and B are small, then those terms can be ignored and you get back the ideal gas law. But if they're not, then you can still take a look and understand some other insights into what's going on. If you have a sparsely populated volume of the gas, that is the volume of the gas is very, very large, then you know that the term on the left of the pressure, this volume will be very large, and in fact, you're going to square it. So this term essentially can be ignored. And again, if the volume is very large, then this term will also be approximately V. And so if the volume is very large, the gas behaves very much like an ideal gas law. You could have a different possible state. Suppose the temperature is very small, almost zero. In this case, we start with van der Waals equation, and the right-hand side of this is near zero. The right-hand side of the equation is nearly zero. So we have no reason to believe that the pressure terms here are small, which means that the volume minus the constant times the number must be small. And therefore, you can conclude that the volume is approximately equal to that. And thus, for a very cold, that is, a very low temperature van der Waals fluid, it's approximately incompressible. Another.
Oh, Bob?
Yeah.
Just before you leave that, I just wanted to point out, as you of course know, that the two terms have physical significance. The term with a B in it accounts for the fact that the molecules themselves occupy a certain volume, so that the volume available to the molecules is the original volume minus the volume occupied by the molecules themselves. And the second term with the A in it accounts for the fact that the molecules may exert forces on each other, which modifies the pressure.
Right. Okay. I was actually supposed to comment about that and I forgot. Thank you.
Sure.
Another non-pressure volume temperature, but related to it, equation of state is thermal photon gas. Now, we've dealt with this when we were doing the Friedman-Robertson-Walker equations in cosmology, where we used the pressure of a photon gas early on in the Big Bang, and this is important there. It's also important in the interior of stars, and it's definitely not anywhere near an ideal gas. For a photon gas, the pressure is just a constant times the temperature related in absolute degrees Kelvin raised to the 4th degree. So, and you can see the constant is complex here. It involves Boltzmann's constant, Planck's reduced constant, the speed of light, and but it's just a constant. So pressure is directly proportional to the temperature related to the 4th power. So not all equations of state behave like the ideal gas. The ideal gas law is definitely not the only game in town. So let's take a completely different kind of equation of state. And in this material, it's the Guth-James law. And it's, if you consider an elastic rope or a rubber band or whatever you want to call it, stretched by a weight in equilibrium. So I've got a weight, this end of the rope is positioned here, fixed here. You've got a weight holding it off. So there's a force going off in this direction. Correspondingly, by Newton's third law, the rope is pulling in the opposite direction. When you're in, if you make this a zero weight so that there is no difference, there's an equilibrium at no weight, and that value is L sub 0. But when you, of course, put a force on there, it's stretched, and so you have L plus delta L here. And this is at any particular temperature in where you're assuming we're in equilibrium. So this equation of state for a rubber band has three variables: the force or tension in newtons, the length, L sub 0 plus delta L in meters, and L sub 0 is the unstretched length of the rope, and T is the temperature in degrees Kelvin. So the equation of state was invented in the early 1930s by Eugene Guth and H.M. James, another typo, that is supposed to be periods, not commas. And the Guth-James one is very straightforward. There's a constant that depends upon the material, the elastic material in the rope, times the temperature times the stretched length minus the unstretched length, that is the constant times the temperature times delta L. So what happens if you were to get a hair dryer and you were going to put it on the rubber band? So in the area around you, you're at 300 degrees Kelvin, but you heat the elastic band. Here's the equation. What does it tell you about what's going to happen to the length of the rubber band if we increase the temperature?
Going to get bigger.
No, it's going to get smaller.
Get smaller because the force goes up.
Yeah, the force is a constant.
Force is constant.
Right. So temperature goes up. A is a constant depending on the material. So if A goes up, delta L goes down. So if you look at it this way, you know, if the temperature goes up, obviously delta L is going to go down. And this is actually a typical behavior for an elastic material.
You heat a bar of steel, it increases in length.
Yes, but
A rubber band like that, if you think of spaghetti. I think the
Whoever
dog,
it is having a very exciting comment.
yes, he's upset with some people making a noise outside. He always has to protect our house.
well, think of rubber bands as a linked spaghetti. and you heat the rubber band, you start causing the spaghetti to vibrate more and more violently. So you have cross-linked spaghetti, and if you have one spaghetti that's oriented north-south and another spaghetti that's oriented east-west, as the east-west spaghetti starts vibrating back and forth, it kinks the north-south piece of spaghetti, causing it to shorten in length. And the north-south spaghetti does the same to the east-west spaghetti. They start kinking up because they are vibrating more and more violently. So that shortens the overall length. Works very differently than a piece of steel.
Thank you, Steve.
I don't know if that helped or not, but
No, it did very much. Thank you.
Okay, so we're talking about a specific, any elastic material?
This is a typical behavior of an elastic material similar to a rubber band. Those kinds of elastic materials.
it wouldn't be any type of elastic material. You could take a steel wire and it has a certain elastic limit, but it doesn't behave like a rubber band at all.
No,
You heat up a steel wire, it would increase in length, unlike if it were subjected to a constant force, it would increase in length, unlike a rubber band that decreases in length.
that's what I started to say is, I mean, that's why roads buckle. When it gets hot, the road buckles because it buckles because it is increasing in length.
Right.
And again, crystalline materials, I think, crystalline solids increase in length when subjected to increased temperature, and particularly if they're subjected to the same axial stresses, the same forces that are holding it, as in the case of rubber band. So this particular material is a fairly unique elastic material.
No, many plastic materials, rubbers, many different kinds of
Polymers
will typically behave this kind of behavior.
Versus, I mean, there are a lot of crystalline solids which are elastic materials.
Yeah,
metals.
But if you heat a crystalline solid, what you're doing is causing the molecules to vibrate about their equilibrium positions and causing them to, on average, increasing their intermolecular distances. That causes the solid to expand. But a rubber band behaves very differently. As I say, you have to think not of individual molecules occupying lattice sites, but strands of like spaghetti.
Sure, no, I understand that, but I'm just saying this is I want to say not a unique class. There are classes of elastic materials which behave just the opposite as this.
Right, like a rubber band. And
yes,
most polymers and the way in which they will behave. But yeah, and not only that, I mean, this equation is only if the stretching, the weight is so small that the stretching is small compared to the equilibrium thing. So there's a lot of limitations in this particular equation of state. But
Bob, can I ask a question?
Sure.
How would a protein behave? A string of protein when it is heated?
I don't actually know for sure, but because they're generally polymers as well, I would expect them to do the same thing. They would, if given a heat, they would shrink. But that's a guess. Do you know for sure?
I believe most meats will shrink if you heat them up.
Okay.
Okay. All right. So next week, we're going to take us to entropy. We're going to develop the ideal gas law using Maxwell's insight in statistical mechanics. And Maxwell made many contributions in thermodynamics, especially in the concept of Maxwell's demon. And we're going to eventually use Maxwell's demon to show us that information is physical and can be the basis of thermodynamics. So this is as much as I was able to get work this week. And if you have any questions, let me know.
Well, Bob, thank you.
Yeah, thank you.
Thank you,
Thank
Bob.
you.
Great.
Very well done. That was excellent.
Thank you. Let's see, I'm going to stop my recording if I can.
Good job, Bob.
Are you going to send out the,
Yeah, I'm going to send out the 2 slide packs,
correct.
although some of them actually have a lot of, if the size is over 5 megabytes, my email won't pass it along. So if they're over that much size, I'll have to put it in a Dropbox and then send you a URL that you can download it from. I apologize, but okay.
Okay, well, we'll see you all next week.
Yeah,
All right.
thank you.
Thank
you.
Okay.
Everybody stay healthy.
Thank you.
Yes, please.
The command.